In this video, we're going to learn what are generative adversarial networks, or GANs. GANs are neural networks that learn to create synthetic data similar to some known input data. They were first introduced in 2014 by a group of researchers at the University of Montreal, led by Jan Goodfellow from OpenAI. After that, GANs quickly gained popularity in the community of researchers of deep learning. Recently, many scientific efforts are devoted to the application of GANs to the tasks of machine learning and to the stabilization of their training. You can compare a GAN with a pair of forger and the police. The forger, or a generator, falsifies money and wants to deceive the policeman, or a discriminator, who in turn tries to distinguish real bills from forged ones. Unlike standard approaches, not only the model is training, but so does the loss function or discriminator. GAN is a generative machine learning model in which two neural networks are competing against each other. Instead of using a standard fixed cost function, we learn the cost function with the neural network. We alternate between training different parts of the network. With GANs, researchers have generated convincing images from photographs of everything from bedrooms to album covers, and they display a remarkable ability to reflect higher-order semantic logic. For example, which of these photos are real? And the spoiler is none. Let's take a closer look at the structure of a GAN. The discriminator takes an image of a bear, for example, and its task is to distinguish whether it's generated by a generator or is it a real bear picture. That is, the output of the discriminator is the probability that the picture is real. The GAN training framework works as if two adversaries were playing against each other in a game. Each player is represented by a differentiable function controlled by a set of parameters, typically a deep neural network. The game plays out in two scenarios. In one scenario, training examples X are randomly sampled from the training set and used as input for the first player, the discriminator, represented by the function d. The goal of the discriminator is to output the probability that its input is real, rather than fake, under the assumption that half of the inputs is ever shown are real and half of them are fake. In this first scenario, the goal of the discriminator is for d of x to be near 1. In the second scenario, inputs z to the generator are randomly sampled from the model's prior or the latent variables. The discriminator strives to make d of g of z approach 0, while the generative network strives to make the same quantity approach 1. If both models have sufficient capacity, then the Nash equilibrium of this game corresponds to the g of z being drawn from the same distribution as the training data and d of x to be 1 for all x. In the learning process, the parameters of the discriminator are adjusted in such a way as to maximize the cross-entropy between the responses and the real classes of pictures. The second part, the generator, takes as an input random vector generated, for example, from a normal distribution and produces a bear image. The task of the generator is to deceive the discriminator, so its parameters are adjusted in such a way as to maximize the discriminator error on the generated pictures. Since the learning processes of the discriminator and the generator occur at the same time, the learning processes of GAN can be represented as the search for a saddle point in a minimax game. Generative adversarial nets are trained by simultaneously updating the discriminator blue so that it discriminates between samples from the data-generated distribution depicted in black and samples of the generative distribution in green. Latent variable z is uniformly sampled noise, and x represents samples in the target domain, say images of bears. After updating the discriminator in a B image, it started distinguishing between real and generated data. Then, after an update to generator in the C image, gradient of discriminator has guided generator to flow to regions that are more likely to be classified as data. After several steps of training, they will reach a point at which both cannot improve because distribution of generator and data distribution are the same. and the discriminator is unable to differentiate between the two distributions. Obviously, for a fixed discriminator, the optimal generator is the one that produces x on any noise vector for which the real probability of the discriminator is maximal. It is also easy to prove that with a fixed generator, the optimal discriminator is the one that gives the ratio of the values of the densities. Estimating this ratio is the key approximation mechanism used by GANs. Most GANs today are at least loosely based on the DC GAN architecture from Alex Radford. DC GAN stands for Deep Convolutional GAN. Though GANs were both deep and convolutional prior to DC GAN, the name DC GAN is useful to refer to this specific style of architecture. Some of the key insights of the DC GAN architecture were to use batch normalization layers and most layers of both the discriminator and the generator, with the two mini batches for the discriminator normalized separately. The last layer of the generator and the first layer of the discriminator are not batch normalized, so that the model can learn the correct mean and scale of the data distribution. The overall network structure is mostly borrowed from the all-convolutional net. This architecture contains neither pooling nor unpooling layers and consists only of convolutional layers. When the generator needs to increase the spatial dimension of the representation, it uses transposed convolution with a stride greater than 1. And third, the use of Adam optimizer was chosen rather than SGD with momentum. To summarize, GANs are an interesting new idea in deep learning, really recent, that is based on alternatively post-optimization problems. So it yields both a generative and a discriminative model. It's fairly hard to train because it features unstable gradients, and nowadays many efforts are targeted at stabilization of their training. And DC GAN lays the foundation for the use of GANs in computer vision.